Good morning, everybody. Our speaker is Madam Śpiewak from our institute, since recently. And the title is Absolute Continuity of
Similar
measures on the plane.
Okay, thank you very much. I will talk about a recent preprint with Boris Solomyak with the same title as the title of the talk. So about this stuff, there are good news and there are bad news. The good news is that the main result which I'm going to talk about is easy to state. And the bad news is that proof is rather technical and it builds very much on works by other authors. So in the end, the stuff will be mostly their or of works in this direction. And the methods which are used at the very end to tell you a bit of what were the technical challenges that we were meeting in our particular case. So the main objects which we are interested in are the so-called self-similar measures, which we consider in 2 dimensions, so on the plane. And let me begin by recalling or defining what these are and also setting some notation. So, okay, so we begin with self-similar measures. I hope that this is quite visible online. So first of all, let me note by this star our basic parameter space, which is just the punctured unit disk on the open unit disk on the complex plane. So these are all the z's for which the absolute value is strictly between 0 and 1. And now, by lambda, I will denote a k-dimensional vector of elements from this unit disk. And by t, I will denote also k-dimensional vector of the complex numbers. So this will be the linear parts or the contractions of the similarities, which will be in our IFS, and this will be the translation parts. And also we need to fix a probability vector. So by p, I will denote a probability vector. Also with k elements, so this is the probability vector. And I always assume that probability vectors are strictly positive. So all the entries are positive. And now by nu, and often by nu with all these parameters, lambda, tau, and p, I will denote the self-similar measure, which we are into. Self-similar measure. And this is by definition, this is the unique Borel probability measure on the complex plane, which is stationary under the Markov process. Oh, sorry, one more bit of notation. So by G lambda I ti, yes, I will denote a map on the complex plane, which is just a similarity with linear part being lambda I. So this goes to lambda iz plus translation pi. Okay, and we consider k such maps. And whenever we are given k such maps with linear parts in this sense, so they are contracting. Then there exists a unique Borel probability measure, which I denote by nu with all these parameters on the complex plane, which by definition is supposed to satisfy the following equation. So mu has to equal the convex combination. The convex combination with weights pi of the images of itself under those maps. Okay, so this is supposed to be equal to the convex sum of pi times g lambda I pi mu. Okay, this just denotes a pull forward of mu via this. So the picture is something like this. And because the maps are contractions, there exists a unique such probability on the complex plane. And the picture is like this. So if we fix, because all of these are contractions, if we fix large enough ball, some B, which is a ball, let's say it's centered at 0 with radius r, then all the scale maps will map this ball strictly into itself, right? So the picture is something like this. So there is a smaller ball inside, which is an image of this large ball under the first map. So I will often denote this simply. Okay, and then maybe there is another ball which is imaged under G2 and so on, and maybe there is some third ball which is disjoint with them, right? And they possibly have different sizes because there might be different linear parts. Okay, and then what we can do is we can iterate this process. So these are, let's say that there are three maps in the system. These are the first level images. First level meaning that under a composition of a single map from the original IFS. So given all this data, we have an IFS consisting of K maps, right, which acts on C. And now what we can do is we can continue this process. So in the second step, we can look at all the images of compositions of length of the maps from this, right? So the second level image will be something like this. So inside G1, there has to be the image of this whole picture, but shrink to fit inside G1, right? So this will be something like image of G1 composed with G1. This will probably image of G1 composed with G3. And so on. Similarly, here, 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 and so on. And if you continue this process, we see that what we obtain is a nested sequence of, well, compact set if the original ball was closed, and in the limit there is a unique compact non-empty attractor of the system. And what we are interested in are some special measures living on these attractors, the one that satisfy this equation. And you can think, I will make it maybe a bit more precise in a moment, but you can think that these measures are obtained in the way that in each step of this contraction, we not only look at the set, but we also distribute measure on them, right? So we start with a unit map. In the first step, we put P1 measure here, P2 of the mass here, P3 of the mass in the third ball, and so on. Here we will put P1 squared mass, P1, P2, and so on. And then in the limit, there is a unique, well-defined probability measure.
Like a limit or limit of averages?
No, just this gives you a sequence of, I will describe the way to define the sequence of measure.
And will it be converged?
Yes, this will converge because of the contraction.
Okay.
This will converge. To set some more notation which will be useful to us and to give you an alternative description of this object, let me define something what is called a natural projection map. So maybe I think I can see it right here. So I will usually denote by I, and this goes from the symbolic space for which the alphabet is just the set 1 up to K. So we will just enumerate all the maps that we have. And
so the question,
yes,
uniqueness of mu is something the standard, right?
yes. So basically, what you do, if you look at the space of Borel probability measures, for example, on some ball, and then you look at the corresponding Markov operator, which sends some measure mu to such an average, and then you see that in some, well, let's say in the Wasserstein distance, which represents the width topology on the measures, because of the contractness, this is not of a contraction. So it has a unique fixed point, and this fixed point is this measure. So what we can also define is the natural projection map, which goes from all the infinite sequences over the alphabet 1 up to K. So this enumerates this codes all the possible infinite sequences of choices of maps from this original IFS. And this goes to the complex plane, and this just assigns to a sequence which I will denote by U1, U2, and so on, the limit as n goes to infinity of the following forms. So what I do is I am given this sequence, I compose the first n maps that was given to me by the sequence, okay? And then I apply it to any point that I wish. Again, because the maps are contracting, this limit exists always and does not depend on the points. Okay, and this is by definition the natural projection map. So you see what it does. It takes an infinite sequence of maps, and the first digit will tell you in which of the three balls that we see here of the first level the point is supposed to be. The second digit will tell us, okay, if we are in the first level, then in which of these three the limiting point will be. And so, and if we have an infinite sequence like this, then this describes a unit point. Okay, and in this language, this self-similar measure nu can be described as the push forward by pi of the Bernoulli measure on this symbolic space. So this is push forward by pi of the Bernoulli measure with the margin, which is this probability vector which we have. Okay. So this is maybe a more precise statement about what I said at the beginning, that we distribute this math at further level cylinder sets. Okay, great. Now, these are quite interesting and often quite complicated objects, the self-similar method. They have been studied for a long time. We know quite a bit about them, but still not everything that we would like to know. Maybe the two basic questions that one can ask about them are the questions of geometrical flavor for this map. So, what is the dimension of such a measure? And if the dimension is full, then whether the self-similar measure is absolutely continuous or not. And these questions are quite easy to understand if there is a good separation in the system. So if for example, on this picture, if the first level balls are disjoint, then I will give you a formula for the dimension in a moment. The difficult stuff is when there are overlaps. So an important notion which we need to introduce is the so-called similarity dimension. Okay, similarity dimension, it depends on this IFS which generates the measure, and it actually depends on the contraction rates and the probabilities. It does not depend on the translations. Okay, and this is by definition, this is ratio of entropy of the probability vector. So minus sum pi log pi divided by the Lyapunov exponent of the system, which is again by definition essentially, well, if you would look at the inverses of this map, then the average expansion that we see in the limit. So this is pi log absolute value of lambda I. And now, so an important fact is the following, that dimension of such self-similar measure nu, in a moment I will tell you what I mean by the dimension, is always at most the similarity dimension. And in fact, if there is this good separation, so for example, if this first level cylinder balls are disjoint, then this is equality. And then the point is that if there are overlaps, then you can think that this value will give you a bound on the dimension in which you, well, neglect the overlaps. But if there actually are overlaps, then maybe you are overestimating your cover that you use to bound the dimension. This is why the dimension can drop. So the actual value of the dimension could be smaller than this upper bound, and it actually happens. There are examples when this happens. In fact, you see, similarity dimension is if, for example, we take many maps, then similarity dimension could be greater than 2. Could be greater than 2. So in general, the upper bound that we get for the, but of course dimension of the measure cannot be greater than 2 on the plane. So actually the bound that we get is that this dimension in general is at most minimum of 2 and the similarity.
Wait, so the similarity dimension ignores the translations.
Yes,
That's all it does.
yes, it does.
If we just take all of them in one place.
Yes, exactly. So if we take, if for example all the maps have the same fixed point, then the self-similar measure is just Dirac's delta in a point. But of course, the similarity dimension could be
something else.
Is something else. So this is the trivial way to get over this. To get the dimension. So let me tell you what I mean by the dimension actually. And this is also essentially a fact. So one can prove that these measures are exact dimension, which means that there exists some number alpha, which in our case, because we are on the plane, is between 0 and 2, such that at almost every point with respect to this measure, the local dimension exists and is equal to alpha. So it's almost surely constant, which means so the local dimension is by definition the limit as r goes to 0 of logarithm of measure of a ball of radius r around x divided by logarithm of r. Okay, and this equals to alpha. Well, maybe I should use mu. Mu almost surely. And then this is what I mean. This is what I mean by dimension. This value alpha is the dimension of the measure, and it agrees with many notions of dimension of a measure. So it agrees with outdoor dimension, with lower and upper outdoor dimension, lower and upper backward dimension. It agrees also with the information dimension. Yes. So, but this of course does not hold for general measures, but for self-similar measures. This is what we mean by the dimension. And now I am able to
remind who proved it.
Well, I'm not sure who proved it first. So there is a general result by Feng and Hu, I believe, which holds in actually a much greater generality than the one that we need here. But for
That if we have limit alpha in this alpha.
Excuse me. So in 2003, it was Deng Feng who proved when all the contraction ratios are the same. And I think that it was this Feng Hu paper from which it follows in the general situation. So self-similar, but maybe also self-conformal. They prove this, and for self-affine it also. We know. I think it was also Deng Feng who proved this for self-affine, that it's exact dimensional. But for self-similar, for sure, for the homogeneous case, all contraction ratios are the same. It's 2003 Deng Feng, and I think 2009 Deng Feng and Hu gives the general self-similar case. So in the self-similar iterated function system, the self-similar measure is exact dimensional. It's Feng Hu 2009, I think.
Okay, thanks a lot. Thank you, Karol. So now I am ready to state our main result. So let me do it right away. So now I switch here. So this is what we do. So what we do is we fix some of the parameters. Well, we actually fix the translations and the probability vector, and we allow lambda, the contraction rate, to vary. Okay, and then the statement is that almost surely, whenever similarity dimension is greater than 2, so we expect to have dimension, well, typically at least 2, then the corresponding such similar measure is absolutely continuous on the plane. Let me state this. So what we fix, okay, first of all, we fix K. K denotes here the number of maps. We fix P, this is the translation vector, and we fix P, the probability. And then the statement is that there exists a set which I will denote by E, that we see, ETP. These are the fixed parameters, and this will be a subset of the supercritical region, which is the following. So these are just all the lambdas. All the lambdas in the, well, k-fold product of this function in disk, such that the similarity dimension is greater than 2. If similarity dimension is smaller than 2, then and of course the dimension has the measure has dimension smaller than 2, so we cannot have absolute continuity. Okay, so this is what often called a supercritical region.
So yes, strictly greater than 2 to have absolute continuity.
Yes.
Equal to the solution.
So equal to 2 is problematic. So on one hand, okay, let me tell you what the statement is, and then I will come back to your question. Now, what's about the set E? So the set E is such that it has Lebesgue measure 0, has 2k dimensional Lebesgue measure 0, right? The space of parameters is 2k dimensional, right? So has 0 Lebesgue measure. And so this is the exceptional set. And whenever we take parameter lambda from outside of this exceptional set, then, well, and if this holds, then the corresponding similar measure, mu lambda TP, let me just write, is absolutely continuous. By absolutely continuous, I mean absolutely continuous with respect to the two-dimensional Lebesgue measure on the plane.
How good density?
Sorry?
How good is the density?
Oh, we don't know. We don't know. So
Standard question.
yes. So something is known about regularity of the density in the homogeneous case. Homogeneous case means that all the lambdas are equal to one another. So there is only one parameter. And in this setting, Solomyak and Shmerkin proved that typically the density is in L cube for some cube greater than 1, depending on all the parameters. Okay.
Do you know anything about the dimension of the exception?
No. So
do you know if it's not non-empty?
Sorry.
Do you know if it's non-empty?
Oh yes, definitely. There are examples where the dimension drops. So you don't have.
Okay, yeah.
You can take all same.
Oh yes.
Same.
Oh, actually, this reminds me that there is a solution which I forgot about, which is that all the elements of this vector are distinct. So, well, there is also an assumption that P1 and K are distinct. By distinct, I mean purposes. So, the reason for which we don't get any information about the density or the dimension of the exceptional set is as I hope to explain you, we heavily use tricks with the Fourier's theorem and whenever you use Houdini, you lose bounds on the dimension or on the density in our cases. And this is the price to pay so far for the non-homogeneous case. And as I will explain, there is a big difference between the homogeneous and non-homogeneous case. So there was a question about what happens when the similarity dimension is equal to 2. So, well, on one hand, the set when this equality holds is itself a zero Lebesgue measure subset of the weak inequality. So for free, I can add it here. The interesting question is, what if I restrict myself to having equality and then consider a lower dimensional Lebesgue measure? This, well, we don't know the answer, at least in our setting, but when you consider this map on R and you take, let's say, only 2 maps, then I think it is known that typically you don't have absolute continuity. So I would expect something similar to hold here, but we haven't really checked. Okay. Okay. So this is the state. And now, as I said, what we do relies heavily, in order to prove this theorem, heavily of methods used by or introduced by other authors. And basically, what we do is we take the one-dimensional strategy, which I will tell you about soon, and extend it to the two-dimensional case, where there are additional phenomena which don't occur in the one-dimensional case, which can make dimension drop and so on. So now I go to the history part of the talk. So this sort of questions, or this sort of results, they were first obtained in mid-90s and early 2000s with the use of technique which is called transversality, which I don't want to talk about because this is not what we use. What I want to say is that drawback of transversality is that it rarely is able to cover the whole supercritical region. So, for example, in 2003, Solomyak and Su, they proved, well, in the homogeneous case, so when all the contraction ratios are equal, with 2 maps, I believe, they proved a similar result, but not on the whole supercritical region, but on a non-trivial subset. On a non-trivial subset of it, there were some. So basically, they couldn't get lambda to be arbitrarily close to 1 in absolute value. There was some upper bound on the absolute value of lambda, which this technique could cover. So this is a limitation. Transversality, of course, has many other advantages, but this is a certain limitation. And a breakthrough came with the works of, from our perspective, with the works of Hochmann. So Hochmann was able to cover the whole, well, basically whole region of parameters if you are interested first in the value of the dimension. Not absolute continuity, but just the dimension. So his result in our notation would be, or in our case, would be stated like this: that dimension of the corresponding similar measure is equal to what you expect it to be. So for us, minimum of 2 and the similarity dimension. And now this is for every lambda outside of some exceptional set. And he did have bounds on the dimension of the exceptions. And in this case, I think this should be so for him. Okay, the packing dimension of the exceptional set is, I think, at most 2k minus 1. This is on the plane. And if you consider, so note that all of this makes sense on the real line. If I treat everything as a real, then I get measures and math and so on the real line. So on the real line, well, so this is on C, and then if you are on the real line, that you have K, not 2K dimensional space of parameters, and then the bound is at most K minus 1. This is an R. This will be important in the moment. And then, of course, you change 2 to 1. If you
So say 0 or?
yes, so okay, so if there are only 2 maps,
Yeah.
then K is 0. Yes. So in particular for Bernoulli convolutions, which correspond to the maps alpha x plus 1.
Mhm.
Let's say alpha is the only parameter, then you get the dimension result outside of a set of dimensions. Now,
But here lambda is parameter and it was past T as a parameter.
no. For Bernoulli convolutions, we consider lambda as a parameter as well.
Okay, but
You can also get
what you were talking about now was part T.
no. Lambda is the parameter.
Not from the beginning?
From the very beginning, yes. So you see, we fix
T is
and we
fixed.
fix P.
Ah,
Okay, and the parameters are lambda.
Falconer is T.
Yes.
Okay.
Falconer is equal for self-affine, and you get typical. You can take typical fixations. Yes. So linear.
Okay, so here lambda is not so it's really.
Yeah. So linear part as a parameter is usually a bit more difficult than translation as the.
Yes, that's what I remember. That lambda, the T is classical, easy. You just translate.
Yes. But of course, from Hoffman's machinery, you can also get results when T is the parameter.
No,
But we are
Thank you.
interested.
I didn't pay attention that you change lambda.
Yes. Lambda is the parameter. This is very important. Now, the next result, which is very important for us, is a result by Shmerkin. So this works are, I think, 2014 and 15. And this is 2014 as well. So this is right after Hoffman. And this is absolute continuity, what we are interested in, but this is on the real line. Now, so the maps are not on C, but on the real line, but they are still just similarities given by these formulas. And he considered only the homogeneous states. Right? So he looks at systems of the form lambda x, maybe lambda x plus T1, lambda x plus T2, and so on. And there are k guys like this. Okay? So there is only one real parameter. There is a one-dimensional parameter, and he proved, that the corresponding similar measure is absolutely continuous for lambdas outside of an exceptional set, and in his case, the exceptional case is of how dimensions. Oh, of course, well, this is all assuming so for lambdas with similarity dimension very quickly.
There was a conjecture that this exceptional might be algebraic numbers.
Well, so for example, for Bernoulli convolutions, the only examples which we know of lambdas for which the measure gets singular are the inverses of the Piso numbers, which are.
But this is conjecture.
No, these are the only examples that we know. And the conjecture is that these are the only examples.
I see, because for Piso it was known.
Yes.
Yes. It was error.
Yes, this is by F dash, and there is also, we also know that actually for Bernoulli convolutions, the dimension even drops for inverses. So
yes,
of the Piso numbers.
yes, I know. This was error.
No, I think the dimension drop was maybe Alexander and.
I think I did it with turbines. Yes, the turbines.
Yes. Okay, so let me tell you what is the strategy of Shmerkin, because it is important for what we do. So yes, so it turns out that the self-similar measures as we will calculate in a moment from this formula, they can be represented as distributions of random infinite sums with independent terms, which means that these measures are some sort of infinite convolutions, and this convolution structure is very important for the technique. So let me see where I can write. Maybe I will write. So we have this definition of the natural projection. Okay, this in my notation, this X should be this. So this is good. So now let me calculate what is this composition in the homogeneous case. So when all the lambdas are equal to one another. Well, so we see that such a composition, right? GU1 composed with GUN of, I will write X because now for a moment we are in the one-dimensional case. So this is just, well, such a composition with n equal n minus 1, and here I have lambda x plus TUN. Right, I have to multiply by lambda and translate by TUN. In the second, let me do one more step. If you take one more step, you see that this is lambda square x plus lambda TUN plus TUN minus 1. Right? Let me see right here. Maybe I can. So now, when you continue like this, you see that the formula which you get is that this composition is equal to lambda to the power n x plus a sum with I from 1 to n minus 1 to n, sorry, lambda I minus 1 TUI. Okay, this is what you I think so. So then if we take limits to infinity, then we see that this projection map is just given by the formula. So as n goes to infinity, this term vanishes, and this is a sum like this. So I will now denote by n. Sum from n equal 1 to infinity of lambda to power n minus 1 TUN. But now we see, if UN is distributed according to a Bernoulli measure, then, well, this sequence lambda to power n minus 1, this is just some deterministic sequence which is non-random. And then the terms here, TUN, they are, well, this is the sequence of IID random variables. Okay, maybe I will use, to emphasize this, I will use a probabilistic notation. So I will say that this is the same distribution as an infinite sum, lambda to power, let me start from 0. So lambda to power n xn, and now these guys xn, they are I and D, and well, the probability that xn equals some pi, this is pi from this original probability. So these are indeed infinite, some sort of infinite convolutions, right? And how to use it? How to use this fact to our advantage? Well, here is what Shmerkin does, or well, the idea. So pick some natural number R, and what we will do is we will split the sum into n's which are divisible by R and the rest. Okay? So I see from this that this measure which I am interested in, well, it is distributed as a sum. Okay, R's, so n's which are divisible by R. Okay. I know it's difficult to distinguish between by R and n, but maybe we will sense. Lambda to power n xn and the rest, right? R does not divide n, lambda to power n xn. But now, so first of all, because all these terms are independent, this means that these two infinite sums are independent as well. Okay? And now on one hand, this guy, so another way to write it is to write it as a sum from n equal 0 to infinity, lambda to power Rn. Right? So this is the same distribution as the measure mu lambda to power R and the same parameters. Okay. Now this guy, on the other hand, let's get some color. This guy, on the other hand, if you take a closer look at it, you will also see that this is a sum of the same type, but just corresponding to a different IFS. Okay, so this is some new, the contraction parameter is the same lambda to power R, and then you have to calculate what is the probability vector and the translation. But if you take a look at it, you will see that this is the case. So this means that you can that this measure is just equal. So this is the same distribution as a convolution of these two guys, right? Mu lambda to power R P E convolved with another guy of the same type. And now, if you also do the calculation by looking what exactly this systems are, you will see that the similarity dimension of the second system, so lambda p tilde, this is something like 1 minus 1 over R, the original similarity dimension. Okay, which means that if we assume that the original system has similarity dimension greater than 1, then for R large enough, also this guy will have similarity dimension greater than 1. So by Hoffman's result, we know that for typical lambda, this will have dimension. This will have dimension equal to 1 for typical lambda. On one hand. On the other hand, by something called Erdős-Kahane method or theorem, it turns out that typical self-similar measure, typical with respect to lambda, no matter what's the similarity dimension, such measure will have power Fourier decay. So let me maybe formulate this because this is the missing point so far in the discussion. Let me get rid of this. So this is something that goes back to Erdős and Kahane. And what we know from them is that, well, in the class of self-similar measures, when you parameterize by lambdas on the real line, then for lambdas again outside of an exceptional set, and again the exceptional set has out of dimension 0. If you look at the Fourier transform of your corresponding measure, okay, then as psi goes to infinity, this will decay like psi to some negative power. Okay, there is some sigma which depends on the parameters, but the point is that it is positive. Okay, so this decay is like constant times psi to power minus sigma. And now the point is that there is an easy lemma, which was proved by Shmerkin, that if you have two such measures, so if you have measure, let me call it mu with full dimension, and you have another measure mu which has power Fourier decay for some positive sigma, we don't care how small it's as long as it's positive. Then the convolution is absolutely complete. Okay, and this holds, okay, this was, I formulated this for dimension 1, but this holds in any dimension. So on RD, if the dimension is equal to D, and then there is power Fourier decay, the convolution will have
mu is what?
So if I have any two probability measures, maybe with compact support, let's say in RD. And I know that one of them has full dimension, and the other one has power Fourier decay. So it has this property for some. I don't care about anything else about this measures. If I get these two properties, then the convolution is absolutely continuous. Now it's
So we don't assume that me is absolutely continuous?
no. That's the point. Just the English. The proof is not difficult. I don't have time to show it to you, but if you know any bit of harmonic analysis,
The decay of the Fourier transform is related to level of singularity.
yes, exactly.
Theorem.
And this is basically the proof of Shmerkin's result, right? Because if I know now that for typical lambda in my class, I will have powerful decay, and for typical lambda, I will have full dimension, then by this lemma, I have absolute continuity. Okay, now, but this is for homogeneous case. So all the parameters lambda are equal to one another, and the same strategy. The exact same strategy doesn't work in the non-homogeneous case, which is our case, and which I am going to explain now. So the next result, and this is the most important result for us, because this is basically what we do is the two-dimensional version of what I am going to give you now. So this is, yes. So this is by Saglietti-Shmerkin-Solomyak, and this is 2018. Okay, 2018. And this is again absolute continuity on the real line, but non-homogeneous. Now, what they prove is exactly the statement, but on R. So lambdas are one-dimensional. Okay, so first, what is the problem with this argument when we are no longer homogeneous? Well, the problem is that then we again have a representation of the self-similar measure as an infinite sum, but no longer with independent terms. And that's the problem. So let me just try to have it somewhere on the board that in the non-homogeneous case, the natural projection mark, which maybe I will parameterize by lambda as well, this is the following formula. So this is sum as n goes to infinity. Yes. Again, we have the term un, but now instead of lambda to power n or n minus 1, we have a product from j equal 1 to n minus 1 lambda uj. Okay, and now different maps have different contraction rates over different linear parts. So when you redo this calculation that we did at the very beginning, you see that this is the term which you get here. And the problem is that now this term is, well, no longer deterministic, it is random, and moreover, the whole terms like this are clearly no longer independent. So we cannot use this. So what is the strategy? And this will be the same strategy as we in the two-dimensional case. So the strategy is something like this. So again, the idea is to take the self-similar measure and decompose it into a bunch of conditional measures. I will tell you how we do the conditioning in a moment, but the point is to decompose the measure mu which we are interested in into some integral of some measures. I will tell you what all of these are, but the point is that now these measures mu omega, which appear in this decomposition, they will no longer be self-similar, but they will be infinite convolutions. Okay, so they will have structure of infinite convolutions, no longer self-similar, but in some sense they will be, that we call it maybe statistically self-similar. So they will be self-similar in some weaker sense. But at least they will be infinite convolution. So for each eta omega, we will be able to play this trick. And now the whole game will be to reprove the Erdős-Kahane result and the Shmerkin's result in a class of measures to which this guys will be. Okay, that's the idea. Now let me give you more details. So how do we perform this decomposition? So we will do it first in the symbolic space. So we will do certain conditioning in the symbolic space. How? Well, so let's say maybe for simplicity, I will just consider system consisting of only two maps, but this is just for the notation to be used. So let's say that we have maps lambda 1 z plus c1. So from now on, I switch again to the complex notation because, well, everything that I will tell you about now, we also have to do in our paper. So this will be G1 and this will be G2. Okay, and now what I will do is I will take an infinite sequence which belongs to the corresponding symbol sequence. So it's over two symbols. And so I have an infinite sequence and I will divide it into blocks of length R. So I again fix some R. So I have the composition, just division into blocks like this. U1 up to UR, UR plus 1 up to U twice R, and so on. Twice R plus 1, and so we are. So I have divided into blocks of length. And so, and now I will introduce, well, formally a sequence of random variables, which are defined as follows. So let me denote by x1 of u. Okay, so I have two symbols in my symbolic space, 1 and 2, and I simply denote by x1 the number of ones, well, in this block. Okay, so this is some number between 0 and 1. Okay, and so by x2 I will denote of u, I will denote the number of ones here, and so on. X3 will be here, and so on. And now first we do conditioning in the symbolic space, and what we will condition on will be this sequence of numbers x1, x2, x3, and so on. So I will simply decompose or disintegrate the Bernoulli measure according to the, not to the order, but to the number of symbols, 1 or 2 in each of the symbols. Okay, so I want to denote by x of u will be just this x1, x2 of u, and so on. Right, and this gives me a random variable which goes from the symbolic space to yet another symbolic space. Well, each of these random variables takes values from 0 to r. So I will denote this by I, and this goes to I to power n. Okay, and I will denote by eta bar omega just the, so I have this random variable, I have measure on the symbolic space, the Bernoulli measure, and I can condition this measure on the value of this host. Right, so this is supposed to be the conditional distribution where I condition on x being equal to omega. Okay, so omega is an infinite sequence from here. Omega 1, omega 2, and so on. This is omega. And this gives me a bunch of measures which do integrate back to the Bernoulli measure. Right? When I integrate them, then with respect to P, which is just projection by X put forward of x by the Bernoulli measure. Okay, and now the point is to understand and now I can tell you what the measures eta omega are without bar, the ones that we are interested in. Well, these are just so eta omega will be put forward by pi lambda of this measure. Okay, eta omega bar. So what I do is instead of pushing forward the full Bernoulli measure, I just push forward a single conditional measure with respect to the number of symbols in each block. And the crucial observation is that now these measures are infinite convolutions. Why is this so? Well, this is so. Okay. So let me denote by this sequences U1 up to UR by V1. This will be V2, V3, this is the composition into blocks. And I want to denote by G, Vj, that's the composition of the maps from the corresponding block. Okay? So these are guys like G, U, J, R, X1, up to G, U, J plus 1. J plus 1 R. And then you can do the same calculation that we already did, or maybe you can redo this calculation. And then you see, well, okay, what will be this map? This map will be some similarity. It will have the linear part and the translation. And now what will be the linear? This is crucial. So I have a bunch of similarities, I compose them, then the linear map, then the linear part will be just a product of the linear parts of these guys. But now you see, to know the product, I only need to know. So in this product, there will be lambda 1s and lambda 2s. But because complex multiplication is commutative, the order doesn't matter, right? It only matters how many 1s and 2s I see in the block. And that's the whole thing. So this will be something like, so I have lambda 1 to the power, well, how many ones I have seen in the J block. So this is in my notation omega J, lambda 2 to power R minus omega J times C, this is the linear part. And then there is some translation which depends on lambda and depends on, well, on these maps that I have seen here. And this does depend on the order, but I don't care. I will just denote it TBJ. Okay? So now, well, if you take this formula and apply it to the R product of the system, we see the following: that pi lambda of U is now okay. It's again an infinite sum, where now the nth term is the product of terms like this. Okay, so this is something like j equal to 1 up to n minus 1, lambda 1 to the power omega j, lambda 2 to the power r minus omega j, and then there are translations which depend on Vj, depend on the order and so on, depend on everything. But the point is that now if I condition on omega, then this is again a deterministic sequence, right? After conditioning on omega. And these guys, well, these guys are still IID and, well, not IID, but independent. Independent because they depend only on the symbols which I see in the J block, but the blocks are independent from one another. Independent from one another, right? So this is why such measure is again an infinite convolution. Okay? And now, knowing this, indeed, proving the absolute continuity result via this strategy requires, well, proving that for typical lambda, for almost every omega, in the supercritical region for almost every omega, this measure will have full Hausdorff dimension and power Fourier decay. So this requires proving some sort of a generalization of Erdős-Kahane and Kochman's result, and this is what those three authors did in the one-dimensional case, and this is what we do in the two-dimensional. So now, how much time? 25 minutes. A bit more. So what I will do now is I will formulate. So actually, we can forget for a moment about this discussion, and I will formulate general results of the form. Here you have a class of statistically self-similar measures, this more general measures, which are not genuinely self-similar, but self-similar in some weaker sense. They will formulate results about those. And this sort of random self-similar measures, they are also of independent interest as well. So now I introduce a setting of what might be called maybe random self-similar measures, and this will be some sort of general class of measures to which these guys will follow. So now, what we will do now is, instead of having a single IFS to iterate, we will have a couple of IFSs to iterate. The advantage will be that each of the IFSs will be homogeneous on its own, but the price to pay will be that now we iterate them randomly. So in each step, I have several IFSs, and in each step, I choose randomly which of them to apply, and then once I have chosen it, I chose again randomly which of the maps inside this IFS to apply. So I will denote by I the finite set, some finite set. The notation is, of course, supposed to match this notation. This notation is this particular construct. So this I will correspond to this I. Okay, and I assume that for each I in this index set, I have an IFS. Okay, I have an IFS which has some number of maps which depends on I will call it AI.
I'm not. You are talking about something new now, or it is?
In a sense, yes. So what I
direct.
Yes. So what I am doing now is I am introducing a more general setting, which will include this sort of particular measure that we have constructed here, and state results in this more general setting, and conclude that this implies in our particular setting implies the absolute continuity. So these are supposed to be homogeneous. Homogeneous IFSs in our case on the context. So this means that they are of the form J map in the I system is lambda I, which depends only on I on the system, D plus some translation which depends on D. Okay, and I also assume that each IFS comes with its probability. So there is some I which is which has K1 terms. KI. Now, omega, which should correspond to the space over which we integrate in this integral. So this is the space I to power n. So this is all the possible sequences of choices of IFS so far. Not mapped from the IFSs, but just a sequence of IFS. Okay, and I will denote. Again, I want to have the natural projection map, which will correspond to this one. So I need a symbolic space. So whenever I am given omega and length n, this is supposed to be the space of all the possible. So once I am given omega, I know the sequence of IFSs. So now I want to consider all the possible choices of maps from this sequence of IFSs that omega describes. So this is what is this? This is a product from 1 to n might be infinity. Well, just of the sets that enumerate maps in this in the JIFS according to O. And then we can define the natural projection map, which will go from the infinite space like this. So for n equal to infinity, so it goes from x infinity omega to the complex numbers, and this is what you expect it to be. So whenever you give me a sequence of maps, which are now from the consecutive IFSs that I've seen here, this is supposed to be the limit as n goes to infinity of f. Well, I am in IFS omega 1, and then I put u1 as the limit here, and I compose like this. F omega n un of any z that I care about, maybe starting from 0. Okay, and this again has the form of infinite series, which is crucial for the convolutions part. And so this is a series like this, T omega n un. It's omega n un. And now, what are the measures which we push forward, which in our case will be these measures eta bar omega, which were the conditional measures when we were conditioning on this? Well, note that even after conditioning on omega, this conditional measure which I see here, then of course the distribution of eta omega bar on each of the blocks of length R, it depends on omega, which was given, because omega tells me what are the numbers of constant. But nevertheless, on this consecutive block, this conditional measure is independent on the blocks, right? Because the number of maps here in this block tells me nothing about the number of maps in all the other blocks, right? So this measure, eta omega, is no longer Bernoulli, but it is at least an infinite product, right? So the general setting is that eta bar omega is an infinite product of what? Well, I have a sequence of IFSs, and for each IFS I have a probability. So I can take a product. So this is product from m equal maybe 1 infinity of p omega. Great. And this is the general setting. Maybe one more thing. This is just notation. Again, eta omega will be pushed forward by pi omega of eta bar omega, just as it was in our case. And now we will call a model. So model which I will denote by sigma. This is a triple which contains the data that is required to define all this stuff. So this is a sequence of IFSs, right? I is from the index set. A sequence of probability vectors, so Pi. And the one last remaining thing, which I haven't told you, is how to. So we have this for each omega. I have a measure, but I also have to choose omega's probability, right? So we will also have some probability measure P. This is a probability measure on omega. Great. So now I can tell you what are the general statements that one can get in this sort of setting on this power Fourier decay and on dimension and what is the dimension result that one can get. And this is probably how far we will be able to get today. So now, okay, maybe first. Okay, there's one more thing which I wanted to note. sorry, I will come back to it for a moment. There is one more thing which I want to note about this sort of general setting of measure. On this random, so now I call it each eta omega is a sort of a random self-similar measurement. But self-similar makes sense in what sense? So they are not only similar, but there is sort of a dynamic self-similarity relation, which is like this. That eta omega can be decomposed in the following way. So, okay, I have omega. This is an infinite sequence of IFSs. I look at the first IFS in the sequence. Okay, and now I sum among the maps in the so I am given omega 1. I look at this map that I can see. So I sum over 1 up to k omega 1. Okay, and now if I look at the probability of the map number u from here, which is in our notation something like this, then with this probability, I push forward by this corresponding map. So this is something like this. And now, if I would write eta omega here, this would mean that eta omega is self-similar, right? But instead, I have to write eta t omega, where t is the left shift on the symbolic space omega. And you see, because there is this relationship, maybe we no longer have self-similarity, but if this measure P is something like ergodic and shift invariant on omega, then we can play with some ergodic theory tools in order to maybe get some results for this sort of measures. And this is indeed what Shmerkin-Solomyak Saglietti did in dimension 1, and we redo it in dimension 2. Okay, so first, not more about it. So the first result will be the Fourier. So the statement is like this: we fix a finite set I, and we fix a sequence of numbers beta I, okay, which are complex numbers and are non-zero and are indexed by elements of this. Okay, and here we fix the measure P to be some Bernoulli measure on omega. Okay, so we choose the distance in an IMD. This is Bernoulli, and now the statement is that there exists a set G, because this is a good set, which is a subset of the product of omega, so all the possible sequences of choices of IFSs with the one-dimensional parameter space. Okay? And this set has two properties. What are the properties? So first of all, it is small, in the sense that for P almost every omega in omega, if I look at the set of lambdas in the unit this, such that we are unlucky, we are not in the good set. Okay, then this is small in the sense of having Hausdorff dimension at most 1. Now recall that the parameter space here is the two-dimensional, so this is clear. And the second thing, the main one, well, okay, both are main. Our Fourier decay statement is like this: that if we have such a pair, and sigma is any, okay, is a non-degenerate model. I haven't told you what non-degenerate is, but let me do it. It just means that at least one of these IFSs does not consist of a single node. Okay, in at least one of them, there are two distinct nodes. That being non-degenerate, otherwise all the measures are there. There is delta and there is such that the ith system in this model, the ith system, has linear part lambda. This is the parameter to power beta. Okay, but we only take such lambdas that this makes sense in the sense that the speed has absolute value smaller than 1. Otherwise, we don't have it. So whenever I have a system which has, whenever I have a model which has a Bernoulli measure V here in the base, and the ith system has linear part lambda to the power beta I, then the corresponding measure eta omega has power Fourier beta. Okay, and from this, so you see that the statement is one-dimensional in lambda, but because we apply, we can fix any beta, we can just well, foliate the k-dimensional parameter space with curves like this, and this is how we get this power Fourier decay for almost every omega for almost every lambda. This is where Fubini's theorem comes into play, and we lose the information on the data. So this is the power Fourier decay part, and now let me go to the dimension part. So in order to so this is an analog of Erdős-Kahane, and now we also need an analog of Hoffman's result. So in order to talk about version of non-dimension drop result, we need to have a notion of a similarity dimension for this sort of models, right? To have something to compare the actual dimension. And this is, so let me define it. So as said, similarity dimension of the model sigma, this is, well, we have a bunch of systems. Each of the systems has its entropy and Lyapunov exponent. We take average entropy over average Lyapunov exponent. So this is, let me just write it like this. This is integral over omega of entropy of the pragmatic vector omega 1, where omega 1 is taken, where omega is taken with respect to p, and the same. Well, the systems are homogeneous, so this is just minus log lambda omega 1. Okay. In all the cases which we consider, the measure P is shift invariant of the domains. Looking at the marginal mix. So here will be the result. Here will be the result.
But in your main result, do you get CI to be different? Is it necessary? Phi I, the systems, they will be different?
No, they don't have. They don't have to be different.
Okay.
They don't have to be different. They can have all the same linear part, all the same translations. Then it's just a statement about, well, okay. Then. Okay. I wanted to like to do.
Yeah, I wanted to say, so in the proof, do you need them to be different, or it's sufficient to have this theorem for by I or all equal?
Well, we don't need them to be, well, okay, in our application, they will be different. Okay, but in general, we don't have to be. If it's, I don't think it's something that we use in the proof of the absolute continuity.
Okay.
Okay, so I need to introduce one more notation to state the result. Let me note by delta omega n, this will be the minimal distance between the nth level cylinders in the system. So in my notation, this will be either, when it makes sense, it will be minimum of the distance between, okay. So first let me write it down and then explain the notation. So I have omega, I take two sequences UV, which are possible choices of maps, possible choices of n maps according to the sequence omega, and I want them to be D, U and D. Okay, and now this distance, so if we take a look at at this initial picture where we have the large ball and then a bunch of smaller balls inside. Let's say that this is nth level generation of the system. Then whenever I take two cylinders like this, I can take a look at the distance between them in the sense of the distance between the centers. And this thing is the smallest difference that I will see. If there are at least, so this is if, there are at least two maps needed, because we also allow for some of the systems to have only one map inside in it. So then maybe there are omegas and times for which there is only one map actually. So this is the length of this symbolic space is at least times. This is one option, and then 0 if designed. So here is the last result. So now, again, we assume that sigma is a non-degenerate model. And here P is P invariant, so P invariant and their goals. And there is one more assumption, which is needed, which does not appear in the one-dimensional case because it doesn't make sense, but it's needed in the two-dimensional case, that with positive probability, we see some non-trivial rotation in this random space. So if we have the positive probability that lambda omega 1 is non-real, is positive. This is, and the point is, well, in two-dimensional case, the whole fight is to make use of this sort of assumption. But as soon as we assume this, then so these are the assumptions. And now the statement is the following: that if dimension of the model, okay, now what is the dimension of a model? We have this bunch of random measures eta omega, and one can prove that almost every of them is exact dimensional, and moreover, the dimension is almost surely constant. So there is some value alpha such that almost every eta omega is exact dimensional with dimension alpha. This is by definition the dimension of a model as such. And now if this drops, so if this is smaller than minimum of 2 and the similarity dimension as defined on the other board, then the system has super exponential condensation of cylinders, which means that if I look at the, well, logarithm of this distance and divide it by n, this goes to minus infinity in probability, which means the same that for every n, the probability of omegas such that this distance, this minimal distance is smaller than exponential with rate n. Okay? This goes to 1 as n goes to infinity. So the condensation of the cylinders is faster than any exponential. Okay, it is always at least exponential just because we are contractions. But if there is a dimension drop, then actually we have super exponential.
Looks like
This is exactly Hoffman's condition. So this is actually a version of a two-dimensional result by Hoffman in the setting of this random measures. And now another thing, so this is another thing that Hoffman observed, but this is the easy part of his results. Then this condition, in terms of parameters lambda, this condition is not typical. Is atypical. So now, if we are back to the original setting of genuine self-similar measures, we do this whole contraction that we did. We get models, we get this result, and then we can prove that for almost every lambda in this k-dimensional parameter space, there exists m such that we have exponential separation. So the opposite of this for some n. this actually for all ometers, right? So this condition, well, this condition and hence this condition can only hold on a set of Lebesgue measures. And now, so I have 2 minutes left. So let me only tell you very briefly, what is the difference between proving this sort of theorem in dimension 1, which is what Shmerkin, Saglietti, and Solomyak did a couple of years ago, where they don't have to assume this condition because it doesn't make much sense. What is the difference between the one-dimensional case and the two-dimensional? The difference is already seen in the work of Hochman for genuinely self-similar measures. And the point is that in 2 dimensions and higher, there is additional phenomena other than the super exponential condensation of cylinders, which can cause the dimension to drop. So in 2 dimensions, it is not true. So this condition is called exponential separation condition. And in 1 dimension, it is true that exponential separation condition implies no dimension drop, but in 2 dimensions, this is no longer true. There is an additional phenomena, and the phenomena can be seen on a very simple example. So let me take an IFS on the plane which sends a unit square into a bunch of small unit squares which are aligned something like this. Okay, so this is supposed to be very similar. So they all have the same and maybe even homogeneous. So they all have the same sign, and they are aligned like this. Almost the same. Okay, and now it is easy to. There are plenty of examples like this for which the exponential separation holds. Because to check exponential separation here, you essentially have to check only exponential separation between compositions of maps which come from the same row, because the columns, like the rows between themselves, are well separated already in the first step. But this is the same as checking the exponential separation condition for the projection onto the line, and essentially by this sort of statement there is plenty of those. So it is easy to find an example for which the similarity dimension is greater than 9. Exponential separation condition holds, but clearly here in the attractor we have the dimension drop, because the attractor is a subset of a product of an interval times some contour set that will be generated here, which definitely has dimensions smaller than 1. So we have dimension drop even though we have exponential separation condition. And what Hochman proves in the genuinely self-similar case, and what we have to with quite some work kind of reprove in this random 2-dimensional case, is that so there is only one additional phenomena which can cause the similarity dimension to drop. And this phenomena can be seen here in such a way that you see if we take the self-similar measure here, so it lives on a product of an interval with a converse. So if we look at the conditional measures in the on the foliation into lines in the horizontal direction, then maybe the horizontal direction is B, and this is some conditional measure mu x. Then the dimension of such conditional measures mu x is equal to 1 for almost every x. For almost every x. Such phenomena is called by Hochman separation. And what he does is he proves that if there is a dimension drop, then we have and the exponential separation condition holds, then the saturation thing must have. And in the self-similar case, it is easy to see that if there is some non-trivial rotation in the system, and the dimension is smaller than 2, which is the case if the dimension drops, then there cannot be saturation in any direction. Because if there is a saturation in one direction, then after applying self-similarity, there is rotation, there is saturation in some other direction, which is which is not the same, which is a different direction. And it's easy to see that if you have a measure which is saturated in two distinct directions, it must be actually of dimension 2. Okay. The problem with, so the final statement from me. The problem in the random case with using the argument that I just told you is that the self-similarity rotation, the self-similarity relation will tell you that, okay, if your measure eta omega is saturated in some direction, then you will get that in some different, that in the rotated direction, the measure eta t omega is saturated in some direction. And a priori, there is no contradiction. And what we have to do is to use some ergodic theory to deal with it, and also rerun the whole machinery of setting of Hoffman in this two-dimensional setting. So I think I ran over time. Sorry for that. Thank you.
Thank you. Do you have questions?
I have a question. So I didn't understand why you need phi I to be different. So say you have just two maps, G1 and G2 in your initial IFS. In application to such case, what will be phi I?
Once more, if I have just two maps.
Yeah.
You are asking how the model looks like?
Yes.
In this particular case, where so basically the case that we have discussed. Yeah. So okay, there was this drawing here that is gone now. So recall what we did. We conditioned on the first on blocks of length r.
So say you have r equal to 1. Can you say r equal to 1?
I have r equal to 1.
That's
Then the model will will consist only of one IFS with your original maps. So then there is only one eta omega, and it's equal to your similar measure. So in this sense, the results for models, they in particular include genuinely self-similar measures which correspond in this construction case are equal to 1.
And if r equal to 2, you already have different.
You already have different. Yes. So the point is what we do is we condition on the number of, let's say, ones and twos in the sequences, which by this calculation that I was kind of doing is essentially the same as doing the following. Okay, I have my collection of maps. I look at all the possible compositions of length r. So this is the bunch of similarity maps, which have some linear parts and some translations. And essentially conditioning on the number of maps is in this bunch of compositions of length r, I condition on the linear part of the composition. So into single IFS, single IFS in the model will fall all the maps which are compositions of length r or of the original from the original IFS. Essentially, the guys which have into one bucket, I will put all the guys who have the same linear part, and then after we condition on this, the only randomness is left in the translation, which depends also on the order, not only on the number of maps in each group. Yeah, and then in order to apply this machinery of models to this decomposition that we were just discussing, you have to calculate the probabilities with which you choose them and so on. But this is basic.
Some more questions?
May I ask a question? Adam, I know that you are very much interested in iterated function system of contracting on average iterated. Is there any chance?
That's a good question. So, as far as I know, there is a problem. So there is no version of Hoffman's result for a single IFS, but contracting on average. I think I know that he wrote in his original paper that this can be extended to the average contracting on average case, but as far as I know, right now he claims that it's no longer so clear how to do it. So, so this would be the first step to get this sort of result for averaging, for contracting on average systems.
So maybe a related question, what if the numbers pi are replaced by functions?
So if
That's
the,
what Claudius Czubek calculated.
yes. Okay, so this would, so this is the case where the probabilities with which we choose maps are place dependent, right? And this sort of measures, they can be realized as well, if the probabilities are smooth enough, Helder or something like this, this measures, so that this stationary measures for place-dependent probabilities, they can be realized as projections from the symbolic space of certain shift invariant ergodic measures, some Gibbs measures corresponding to the potential which comes from the probabilities. And now, well, I don't know much about the Erdős-Kahanes or the Fourier decay part, but the Hofmann's result was actually extended to projections of orbits in one dimension. This is very important. In dimension one, it was extended to the case of projections of arbitrary fixed invariant ergodic measures from the symbolic space. This was done by Jordan and Rappaport, but so far this is not done in dimension higher than one. And the reason is that they prove uses, so okay, there is this whole theory of Hoffmann for the Hausdorff dimension of the measure, and there was an extension of this by Shmerkin to the LQ, dimension. But the point is that his work is done so far only in dimension one. And as far as I know, there are no results of this sort in higher dimensions, and I think that Shmerkin claims that this is technically difficult. So maybe in dimension one something could be done, but again, well, the question is for general ergodic measures, how the convolution structure looks like, right? Because here, these measures at omega that we look at, they are of course much more general than projections of Bernoulli measures, but they are still projections of product measures. And now if instead of Bernoulli we start conditioning some general ergodic measure, then it's not done so far. I don't know, maybe this will be pushed forward, but we haven't thought about it. Yes.
More questions? More questions, so thank you very much. And I hope there are